Hello and welcome to Foucault's pendulum for advanced experiments number 7. In today's experiment, well, it's not going to be an experiment, it's actually a problem that I need solving. And the problem is this: it's a problem I need your help for. So if anyone can help, please contact me via the comments. The problem is this: I have a new Static Pleane Pendulum number 2, Static Pleane Pendulum number 2, and the problem arose with doing as I discussed in number 6, I would be looking at the twine or the string or the cable or the fishing line that holds the pendulum to the roof. And in that experiment I had a pendulum swinging for several days, or hanging for several days, and it never moved, except the string got longer, which I was going to show you. That was a demonstration. The string would move with varying in humidity. And in my little, beside it, I had to have my small demonstration where I had the pendulum swinging in that rotary system as I had in video number 1. However, this is the ideal situation where everything's square, but in reality the house is not quite square. It's like one wall's longer than the other. The floor's level because in my lab, because I poured that myself, I know that's level. So, however, the walls and the roof aren't quite level. And I didn't think it was a problem until I encountered this turning situation. Now, when I made my little turning disc, I made a small error of less than 1 millimetre concentricity in this between the centre shaft and the disc. 1 millimetre at this side, less than 1 millimetre at this end. However, at the top, it was about a 10 millimetre error. Now, for experiment number 1, with the first video, it wasn't an issue. It was to merely show you a decoupling experiment. However, when I encountered this problem again, it is a problem I have never seen. It's as I said, it's of gigantic proportions in physics. So please help. Okay, let's go to the setup now, and I'll show you in more detail as we get more data for you to analyse the problem. Right, so here's the setup. As I discussed before, our string experiment, which was to show you the sag over several days, and this gap would get smaller. This pendulum had been here for several days, and the only thing that's moved is the gap's got smaller as the string stretched with humidity. On the right hand side is our analogue showing the setup where we're simulating the earth revolving on this carousel. So here's the top of the roof of the house, and here's the floor, and here's the earth turning. And as I mentioned, the error between the centre shaft, the vertical shaft, and this mounting disc which holds these struts is 1 millimetre. However, over this distance of 400 millimetres, it gets amplified to about 20 millimetres. Now, therein lies the problem. I don't know of a house that is that accurate with a floor and roof ceiling less than 1 millimetre in concentricity. So, you know, what's going on here? So, alright, let's just now move to the dial indicator, and I'll just show you this run out, which may help you process the data. So stand by as I set up for that. Alright, I've just zeroed the dial indicator, and we're getting 0.04, 0.08, 0.1, 0.16, 0.17, 8, 0.2, there's a bit of a flick there. Alright, back to where we started. Possibly, maybe even less than 1 millimetre. Alright, so there's the concentricity error, which is pretty hard to get out, I can tell you. Alright, let's go back and continue with our problem. Right, so here we are with the problem. Two pendulums, one attached to a roof, one attached to a simulator, simulating the roof and the revolving earth below it. When I revolve this one, simulating the earth moving, the pendulum moves off the centre dot. It moves away by at least 10 millimetres, sometimes 15, maybe 20 millimetres. However, this pendulum does not. Why, when the earth goes around with this pendulum, why doesn't it move? This is the same simulation. This is the earth spinning. Here's the roof, same pendulum. However, I get a movement in the pendulum. There's no need to swing it. Quite obviously, you would see a deviation off the centre point. So, that is my problem. Now, you might say, well, you've just spent 6 experiments showing the importance of having the pendulum swing to decouple. Well, it doesn't seem to be a problem. Let's just zoom in on the top. It's not as if it was fixed and undecoupled. So let's go to that now. Well, at this slow speed, the top bearing is coupled. So we don't even need the magnetic coupling. We could just use a fixed point, a fixed keyed point. Okay, hopefully that might help you with some more data. Alright, the next bit of data that may help you is it is impossible to line this pendulum to that point. In simulation, mathematically it's possible, but to do it in practice it's impossible. No matter how I adjust this disc up or down, I can get it right in one spot, but the moment I move it just a few millimetres around, it varies again. It's like trying to balance a pencil on a pencil. So what we're trying to do is we're trying to balance the tip of this, lower it without using the wire connecting it. What we're trying to do is balance this on top of that without the wire. Impossible. Okay, maybe that can help. Okay, you can see my dilemma. Video number 8. I was going to probably ask you people to go out and buy some exotic optical cable or some exotic pendulum, or spend a lot of money, and really all you need is a rock and a piece of rope. So before I can go on to video 8, I've got to solve this problem. If you just need a tripod with a slightly tilted base, you won't need to go and buy an optical ring laser. So what am I missing? My physics isn't that good and my maths isn't that good, so I need help. But one thing I did forgot to mention, maybe it's scale. The pendulum in Paris is 67 metres long, so maybe over those distances this doesn't work, or this effect doesn't come in. And I guess there's only one other thing left, and that's, look, I won't say it, but I'll just point to it. Okay, well, thanks for watching, and hopefully we might see you in video number 8. Thank you.